Okay, so in this video we're going to look at the simplest case of projectile motion. We're going to try to understand what happens to an object when it's launched horizontally from some height. We're going to describe the motion. We have two things going on at once. It's going to move forward and it's going to fall. And then we want to be able to look at where it is at specific times. And that where has two components. There is a horizontal component and a vertical component. So we have a little table right here that's going to help us keep track of that. And then we're going to summarize all this by looking at an equation that summarizes ultimately how far an object will land away from where we launch it and be able to determine how much time something's in the air. Okay, so we're going to build this lesson around an example. We have a cannonball fired horizontally, so that's a key component right here. And we're at a high cliff. It's fired at a speed of 10 meters per second, and we're assuming negligible air resistance. Okay, another piece of information here, so we want to know what the trajectory will look like. Okay, so the cannonball starts right here, and then at some time later, it's going to be on the ground. We understand how the path it takes, how far away it lands, and even how high it must have been in order to hit the ground at 5 seconds later. Okay, so in order to do that, we have to understand what's going on horizontally and vertically. So to understand the horizontal, it's pretty straightforward. Horizontally, there is nothing acting on the cannonball once it leaves the cannon. If we neglect any effects due to air resistance, while gravity is trying to pull it down, that's vertical, there's nothing horizontally. So we can say the horizontal motion is constant. And that's a key, a very important point. Whereas the vertical motion, we've already established from our free fall, is continually accelerating. All right? So we have two very different types of motions in the directions. Forward, it's constant. Vertical, it's accelerated. So when we go to calculate where it is at different times, we have to be careful. So let's turn our attention to this chart right over here. Okay, I've got times 0 through 5, and we want to see where it is horizontally and where it is vertically. Plot the cannonball at those places, and then put it all together. Okay, so let's take the fact that the constant. So if we have constant motion, we can talk about where it is in the x direction. So we're going to call x rather than d. And we can say simply that x equals vt plus 1/2 at squared. However, since it's constant motion, this term is 0, so our horizontal position is simply how fast we're going. So we can put the bar there, multiplied by the time. So let's do that right now. So at time 0, our position is 0. Okay. After 1 second, if our velocity is, if our x is equal to v times t, as we said earlier, right? So I can just put right above here, v times t. We can do a speed of 10 times 1 is 10. Speed of 10 times 2 seconds is 20, and so on and so forth. So we have that. And so if we had no gravity, the ball would be here, then here, then here, then here. All right, so that's times 0, 1, 2, 3, 4, and then let's put a 5th second right around there because I didn't complete that. Okay, now, so we see it's equally spaced, nothing surprising about that. What's going on vertically? Okay, so vertically, we have to treat this as accelerated motion. So let's develop an equation right down here. So vertically, we're going to call vertical displacement y, okay? And we can use the same equation we used before, equals the original speed in the y direction now, times t, plus 1/2 at squared. Okay, now we're going to ask ourselves, is there any original speed in the vertical direction? Well, if it's fired horizontally, then that's a way of saying no. Okay, so that goes to 0. And what's our acceleration in the vertical direction? Of course, that's g. So our vertical position any given time is 1/2 gt squared. Okay, so that's pretty straightforward. If we go to our chart and we put 1/2 gt squared, then we can fill in the numbers. So I'm going to use 10 for g to make our lives a little bit easier. In a real problem, you use 9.8, but they're close enough. So if I put in 1, so times 0, our height is 0, or at least our change in height is 0. Actually, let me think about that. Okay, so instead of calling this y, let's call this delta y, how far we've fallen. Okay, so after 0 seconds, we've fallen 0 meters. After 1 second, 1 squared is 1, times 10 is 10, half of that is 5, so we've fallen 5. So if we go over to here, where the dot is, and we go down to the first hash mark, which is roughly 5 meters, then we're right about there. Okay, so that mark right there is right around 5 meters. All right, if we go to the second, that rhymes. 2 squared is 4, 4 times 10 is 40, half of 40 is 20. So after 2 seconds of time, we have fallen 20. So if this is 5, 10, 15, 20, go over, and we're right about there. Okay, and what you should notice is in this interval we fell 5, and in the next interval we fell a 15. So we're falling a greater distance per interval, as we would expect with with accelerated motion. All right, so if we plug in 3 seconds for the gt squared equation, we get 9 times 10 is 90, 45. If we put in 4 seconds, 4 squared is 16, 16 times 10 is 160, half of that is 80. And then after 5 seconds, we would have 25 times 10, 250, 125. And this total height, I guess we should have mentioned, is 125. So let's put these numbers in. So here's 5, 10, 15, 20, 25, 30, 35, 40, 45. Comes over to right there. 50, 55, 60, 65, 70, 75, 80. Comes over to right there roughly. 85, 90, 95, 100, 105, 110, 115, 120, 125 should be right just before we hit the ground. Okay? And so, based on this information, the object is in the air just over 5 seconds, and we look at the positions, and then we can trace it, all the points between, and we get a very nice looking parabola. And so a very important concept with projectile motion is anytime you project something forward in the air, it doesn't matter whether it's horizontal or even vertical, or excuse me, at some angle, you're always going to get a parabolic shape. And the parabola comes from the fact that, if you want to know why it's always a parabola, it comes from the fact that the x direction is constant motion, but in the y direction, it's accelerated. So whenever you have motion in 2 directions, where one is accelerated and the other is constant, you must get a parabola. We could do a mathematical proof, but I think you'd be fine without it. Okay, so let's summarize the equations that will help us figure this out. So there's 2 things that we want to understand generally with projectile motion. The range. So range is simply how far away in the horizontal direction we are. Okay, and so since we're talking about the horizontal direction and we know horizontally we have constant motion, the equation is pretty easy. We can say that our range, which I'm going to call x, is simply equal to how fast we're moving in the x direction multiplied by how much time we move in that, and that's generally the amount of time in our air. In other words, range is assume that you've hit the ground sometime later. So if you take the amount of time in the air multiplied by how fast you're moving horizontally, and that's why you need the x subscript, then you've got the range. So it's pretty straightforward. The air time is a little bit more involved. If you recall from the lab we did earlier, the time in the air, okay, does not depend on your initial velocity in the x direction. Okay, so if we go up and talk about this cannon and we fire it faster and faster and faster, it's still going to be in the air the same amount of time. We verified that in class. So the time in the air has nothing to do with how fast it's moving forward. Instead, it depends on how high we're dropping it from. The taller the cliff or the higher we drop it, the more time it's going to be in the air. So we want to develop an equation that's going to tell us the amount of time in the air based on height. And in fact, if we stay right here, we can see that this equation will really help us out. Let's reanalyze that. Basically what it's saying is, I want to solve for time in the air. What do I know? I know how high I'm falling. I know the rate at which we're accelerating. We're always accelerating down at 9.8. And then we also know that our initial velocity in the y direction is 0. So I can take this equation that I've got boxed here, I can rearrange it and solve for time. So if I move the 2 over, I've got 2 times y equals gt squared, divide by g, and then take the square root, and I've got an equation for how much time you're in the air when you're projected horizontally from a height. So we can put in here time in the air equals radical 2 times y all over g. And in fact, this equation would work if we just drop something straight down. So it's nothing more than a variation of the kinematic equations that we've already dealt with for free fall. Okay, so some simple problems we can do here. Let's have the equation. So we have an arrow leaves a level bow at a speed of 45 meters per second. So let's start labeling this. The speed is a v, and now we want to be careful. What direction? Well, since it's level, right, we're going to call that Vx, and it's an initial speed, but we need to put that. And the initial height is 1.5 meters, so that's a y. So we don't want to mix up x and y values here. We want to always keep them separate. So I'm going to make a little table, right? Here is my x table and my y table. So what do I know? There's distance, there's time, there's initial speed, and then there's acceleration. So in the x direction, I'm looking for distance. In the y direction, I know it's going to be 1.5. The time, I don't have the information about. The initial speed, this is 45. The initial speed in the y direction is 0. The acceleration in the x direction is 0, and the acceleration in the y direction is negative 9.8 meters per second squared. I should put the units, but I'm not going to here. Okay, so I want to know how much time the arrow will be in the air. So I don't know it. And I need 3 pieces of information. I only have 2 in my x column, so I'm going to use my y column. And in fact, we can use the equation that we developed right here. So we can say time in the air equals radical 2y all over g. So that's going to equal radical 2, the height is 1.5 meters, all over 9.8 meters per second squared. Okay, you can punch the numbers in your calculator. All right, if you do that, you should get 0.55 seconds. Okay, which kind of makes sense. A height of 1.5 meters is like our lab heights, and those balls or marbles are in the air for less than a second. Next question is how far away? Okay, how far away is our distance in the x direction? Okay, this guy right here. So I've got my same table of information, but now I can add to it that the time it's in the air is 0.55. And I can put that right there. So I do my kinematics and I see that I can use this range equation right there, and I can say x equals Vx time in the air. Vx was given as 45 times 0.55 seconds. Multiply those, it's pretty straightforward, and we get about 25 meters. Okay, and the last question, what will be the horizontal speed, Vx, just before it hits the ground? Well, if I go over here, what do we know about the horizontal motion? The acceleration is 0. So that means that our final speed is going to be the same as our initial speed in the horizontal direction, which is 45 meters per second. Okay, the problems get a little bit more complicated from here. So what I want you to try to do on your own are problems on number 2. We'll do 3 together as a class. The answer is given. In fact, if you want to get ambitious, try number 3 as well. Like I said, the answers are there on your note sheet. Okay, good luck with that.